Thank you, everybody, for coming to the session on advances in biogeochemical sensors. I hope to kind of give you an overview, a very high-level overview of what has happened since the last ocean business at Seabird in terms of improvements on biogeochemical sensors. So I'm going to keep it very high level, and we're going to kind of jump a little bit from topic to topic. So really take advantage of asking questions as we go, rather than kind of saving them for the end. For those of you who don't know me, I'm Jochen Klinke. I've been with Seabird just over 6 years now. Initially joined in the product management department, and I've been in my current role as Director of Science probably since 3 years, since the beginning of the pandemic. Is this working? Oh yeah. So today we kind of take a little bit of a tour through the different types of BGC sensors, what they are and why they are important, and on what kind of improvements we have done over the last 3 years, actually 4 years, to sensors and existing products, but also what kind of new products have we launched. And normally I would stop there and not go any deeper than that. But I've gotten a lot of questions about pH over the last year and even yesterday. So I figured I'm going to take a little bit of a chance and also talk about pH improvements, even though we haven't launched a new product there, but at least kind of give you a little bit of insight of what's going on at Seabird with regard to improvements on pH sensing. So as I said, since I'm going to be bouncing around a little bit, feel free to ask questions after every section or during the section. So that's hopefully makes the most sense. Also for people who ask questions, I have some swag. The first person in every section who asks a question is going to be really thankful for a warming scarf. And so we have 4 sections, so like 4 scarves to give away. So talk about BGC sensor. How many of you kind of have used BGC sensors? Oh, quite a few. How many of you know how many essential ocean variables are listed in the BGC Argo science plan? What are the really essential ones? Oh, 6. 6. Oh, you just took it away because I was going to give some hints and ask the group, and you just really cut right to the chase. You know, yeah. The correct answer is actually 6. How did you know that?
Because I work with BGC data every day.
Oh, okay, never mind. Okay, so then here's the more difficult question for you. And since you asked, I think you deserve a warming scarf. Can you just pass it along? My God, the scarf's even hot from the sun. So I'm going to put you to the test now. What are they?
DO, pH, downwelling irradiance, chlorophyll, backscatter, and nitrate.
Wow, you're right on top of it. Got them all right. That's pretty amazing. Awesome. I thought this is going to be a little bit of back and forth, you know. So we just sped up through that section. So you can actually see 5 of the 6 sensors on one of our BGC Navis floats. The sensor that's missing is the irradiance sensor here. So coming a little bit back to why is it important to do improvements, it really aligns well with our mission at Seabird, you know, powering science-based decisions for a better ocean. So it comes natural to improve sensors all the time. And we do this by really collaborating with researchers in the ocean field, in the ocean technology field, because the difficult part of improving a sensor is really the validation. Just designing it in the lab and making it work there is the easy part. Taking it through all the spectrum of conditions out there, that's when you find out if it really works or not. So we are partnering with a lot of researchers across the field here to kind of make these sensors better. BGC sensors are especially important in terms of producing data that will help us understand climate change, global warming, and especially the BGC sensors, understanding the carbon cycle and ocean acidification. So they're really essential. It's kind of a great time to be in this field, to actually work there, to help our understanding. And these data also support the goals of the UN Decade of Ocean Science that we're currently in, with regard to expanding the global ocean observing system, creating kind of a digital representation of the ocean, delivering data, knowledge, and technology to all. And hopefully that will change a little bit how we kind of interact with the ocean in the future. For those who don't know, in 2020, the National Science Foundation funded a program, a multi-million-dollar program called the GoBGC program, to deploy 500 BGC-capable floats by 2025. So at Seabird, we're really kind of focused on making that happen both from the sensor side, but also from the capabilities of our BGC Navis float. So our first stop is going to be on the HydroCAD EP. We came up with a new version. It's called the V2. It's very creative. It's probably, apart from the BGC Navis float, one of our sondes that has the most BGC sensors integrated. Hence, it's called a multi-parameter probe. So this is shown the original version. It's really very similar to a MicroCAD CTD, if you know what that is, with the CTD and a internally pumped system that includes a DO sensor. You can also see that we managed to integrate a glass ball pH sensing element into that float path there. And there's attached a 2-parameter chlorophyll fluorescence and turbidity sensor attached to the probe as well. So it's a really compact system. Has the advantage that you don't really require field calibrations. You can achieve deployment times of over 3 months by swapping out the glass ball pH module. You also have the ability to kind of do field calibrations, 3-point calibrations of the sensor if you so desire. I think one of the big advantages is that it's equipped with anti-fouling, both on the internal flow path through the pumping and actually the TBTO anti-fouling, but also the bio-optic is protected by a copper faceplate and a bio-wiper. If you want to do field calibrations of the pH sensor, you can use a software that's called UCI. It's really designed to be used in moored applications to a maximum depth about 350 meters. And anybody who's deployed sensors in moored applications know that biofouling is an issue. And you can see that on the right side. You can see the sensor on the left before deployment. And the next 2 pictures are a month after deployment and up to about 3 months after deployment. What you see also is that our kind of anti-fouling technology does not really, works really local. So it really works within the water volume, not so much on the outside of the probe. But it ensures that even after 3 months, you get good and accurate data within spec. I think that's one of the big advantages of the system. So I said we came out with a new version, and that was really geared more to improve the ruggability and the reliability in the field. There weren't any particularly accuracy improvements of the sensor or anything like that. It was really just about making it more reliable in the field. And this was really done by kind of redesigning the way the pH module is integrated into the flow path. If you have ever used a MicroCAD CTD, you know that the flow path is a fairly constricted area already, so integrating a sensor into that is not very easy. So we completely redesigned that, really to improve the corrosion resistance against saltwater on the redesigned pH module. You can also kind of field service it by flushing this volume out more easily than before and integrating it in a more secured way where it doesn't leak. So these are really the main improvements on the HydroCAD EP. We try to maintain backwards compatibility in the sense that if you have like a deployment configuration, there's no change to outer diameters of the instrument. And also, if you want to upgrade your sensor from an original system to the new system, you can reuse your DO sensor and the optics also. So there's no changes to that. One thing I kind of want you to take away is today, if you just remember what is new since the last ocean business, I'll be very happy with that. If you can also remember what the change was, that's even better. If you also remember what is actually better about it, the new version. That would be ultimately the bonus for me. So if there's only 4 sections, if you can try to remember what's new, how is it different, and why is it better. So maybe stopping here for questions on the hydrocarbon PV2. You want the scarf, right?
Does the system contain individual components for each parameter, or do you return the whole instrument for calibration?
You return the whole instrument for calibration.
So there's no like hot spares for components?
Except for the pH
Okay.
module. So you can basically have multiple pH modules, and you can just swap that in the field. That's why we made it flushable. You know, there's access holes to kind of clean out the chamber where it's retained. And yes, you can actually do that.
Can I ask a second question, please?
Sure.
What is the
You only get one scarf though.
Yes, Eric and I were talking earlier about the flow rates with inside flow instruments. We used a pump system in the ship
Yes.
at 1.5 meters per minute. Is that too high flow for?
This system is actually pumped by itself at 10 milliliters per second. So you were trying to think about integrating it into a flow-through system?
Yes, of the ship. But we could subsample.
Okay. That's probably a very new application. You almost deserve 2 scores for that. Here we go. Yeah, maybe just kind of we can follow up on that, what potentially the challenges are going to be. Yes, another question?
Is it able to not have the flow through like adaptation on it? Because we used the CFIT in like an underway setting, and we just took off the flow through bit of it and just had it in the underway system. So maybe that's how to answer this question.
Yeah, I think it depends a bit on the situation. I think typically that would not be the right application for this instrument. Yeah. But we can explore kind of what the limitations are on that. We want to stop by the stand or so. Okay, we're going to dilute it. Our next stop is going to be biooptics, and I'm going to keep this very basic because I am not an optical scientist. Luckily, we have our senior optical oceanographer from Seabird in this room, so I can redirect all the difficult questions to him. So, it's not changing, is it? Our first stop is going to be the new version of the LED ACS. It's a sensor that measures attenuation and absorption, as the name suggests. And we did some improvement on this sensor that I'm going to cover very high level. So in simplest terms, the color of the ocean varies based on its constituents. Even I can understand that. So I think I'm trying to keep it that simple. So this instrument makes use of that fact. So the ACS is a system that has, shown here on the right here, it's a flow-through system. So it has 2 flow paths, the A and the C component. And you can see the A is for absorption and the C is for attenuation. We know that light, as it enters the ocean, kind of is absorbed differently depending on the wavelength. So you can see that the highest absorption obviously in the red side of the spectrum, and here on the left side, blue is the least absorbed. That's why ocean water is blue. On top of that, we have the highest scattering in the blue region, but the lowest scattering in the red part of the spectrum. That adds to the fact that the ocean is blue. The instrument consists of an incandescent light source that is run through a linear filter wheel that rotates in the system. You can get it in 2 different path lengths. One is 10 and one is 25 centimeters, depending on your application and your level of constituents that you anticipate in the area that you're working on. That linear variable filter covers the whole visible range from 400 to 730 nanometers with a kind of a bandpass resolution of 4 nanometers peak. And I think the wavelength is about 15 nanometers. You can do very high frequency sampling at 4 hertz with this. Anybody has used an ACS before? No. So the improvement there was really about replacing the incandescent light source with a white light LED source. And there's a few advantages to that. It increases the lifetime by about a factor 2 to about 10,000 hours. It also improves the signals to noise ratio, especially in the blue part of the spectrum. That's a huge advantage compared to the original incandescent light source. On top of that, LEDs typically have a lower power consumption. And they age typically slower, especially in the blue part of the spectrum. Eric, if I say anything wrong about this, please feel free to chime in and correct me. So that's really the main change on the system. The advantage, obviously, of the increased lifetime is that you don't have to send it in for service as often. So I've talked about field validation of instrumentation. That's like the really most difficult part of things. So this LED ACS was integrated on a sailing ship into a flow-through system that contained a thermocylinograph, an SPE 45, if you know what that is, CDOM, and it also had the ability to switch between a filter and the ACS, so you were able to take samples of the constituents in the water for high pressure liquid chromatography analysis, so you can kind of have reference samples and compare the results. The tower took, I think it was a 6-month voyage across the globe, and you can see on the blue dots, that's where ACS measurements were taken, and you can see on the green dots overlaying on the blue dots where the HPLC reference measurements were taken. So there's an example shown of the data here in magenta of the ACS absorption spectrum, and kind of a modeling of that spectrum as if it were the result of overlaying individual kind of functional phytoplankton groups. Here you can see, I think it is 11 total. And what's shown here for a given kind of modeling of a phytoplankton group, and I think it's chlorophyll B, you can see the correlation between the HPLC measurements as a function of concentration with the absorption. You see a pretty high correlation of about, 80? A regression factor of about 80. So this is really a great tool potentially to do in situ validation of ocean color. There's a new ocean color satellite, PACE satellite, is going to be launched at the beginning of 2024. And so you can have potentially an instrument as a very simple way to do absorption measurements that you can correlate with ocean color. And also kind of validate potentially models of different phytoplankton groups as they develop over time. And what's shown here is a Darwin model. If I can find a mouse that shows basically the evaluation. I'm going to turn that sound off. That shows a model of 4 different functional phytoplankton groups as they develop in space and over time. And Eric, do you want to kind of annotate a bit? I know you're familiar with this.
Sure, if some of you attended the presentation before, it'll be a little bit of a repeat, but typically when phytoplankton blooms, you bloom in, let's say, larger species. So I think that's the, whichever one is labeled diatoms. I can't read it from here.
I think it's the bottom on the red one.
Yeah, so, and then naturally as those phytoplankton come to the end of their life, typically because of nutrients being exhausted, you'll have a succession of species, just like you have in any ecosystem. And so that would lead, for example, to the flagellates, the yellow. The 2 others are marine bacteria. They're very small. They're very efficient at scavenging nutrients, so you also find an increase in those. And they play an important role just in the whole ecosystem of carbon storage. Even though they're very tiny, understanding these, and it really wasn't until 1980 we really understood that the last one, the Prochlorococcus, the green, was the most numerous photosynthetic organism on the planet. So with that in mind, you can take a look and see how those evolve over time. You can see the effects in the specific of essentially what are physical waves that go through the ocean, creating that wiggly spot near the equator.
Thanks, Eric. Really appreciate it. Our next stop on biooptics. If I can get there. Is a release of a new dual fluorescence 435, 470 ECO. Anybody know what ECO stands for, the acronym? I know you know. It's environmental characterization optics. To be honest, I would have not guessed that either. So what's shown here is an eco triplet at the bottom with traditional 470 chlorophyll excitation and the turbidity at 700 nanometers on the right side of it. And normally this triplet eco would contain on the left side a CDOM or an FDOM a sensor. In this case, this has been replaced by a 435 nanometer chlorophyll excitation. So you kind of have a dual excitation for chlorophyll here. And this is done in the hope of kind of improving the chlorophyll measurements going forward by exciting specifically chlorophyll A more targeted. And you can see why we think that works is shown in the next slide here, where you can see the 470 is the traditional measurement, and here you can see the absorption spectrum of chlorophyll A, and you can see all the additional pigments that also get excited by the 470. And by shifting down to 435, you can kind of more specifically target the chlorophyll A part of the absorption spectrum, and basically inside the fluorescence there. Eric, anything to add there? Yeah. Thank you. So that was really coming at the request of some of our BGC Argo users to incorporate that, because they think there's maybe a chance to decrease the geographic variability of chlorophyll measurements overall by having this kind of dual measurement of the existing 470 and the new 435. So this was the capability of adding a 435 to the eco triplets was added in early, I think, 2022. And the way we kind of sell it right now, it's always paired with the 470. So you have kind of a reference measurement that gives you kind of the consistency of the global data records, at least for comparison. I think most of the ecos, we call them internally FL, BB, FL, so fluorescence, backscatter fluorescence, are currently deployed, I think, on Apex floats.
Apex, and there's some on French Probor floats and KE floats.
Yeah. So before we stop and switch topics again, any questions? Okay, next up, we're gonna leave biooptics and we're gonna go to dissolved oxygen. So at the beginning of 2020, we were approached by some of our BGC collaborators about updating our optical oxygen sensor on the Navis float. Typically, you can see we have an SPE 63 optical DO sensor integrated into the CTD head of the Navis float. This sensor has the advantage by being integrated into the actual flow part of the CTD. It's protected from biofouling. And I think the main advantage is that you have a better time response of the sensor because it doesn't have to deal with what's called boundary effects. The disadvantage is that typically sensors in this application are deployed for years at a time and drift. So you don't have the ability to correct for that drift because the sensor is integrated into the flow loop. Other manufacturers offer what's called in-air calibratable optical sensors that are attached to the top of the float, and whenever the float comes to the surface, you can do kind of an in-air calibration and correct for that drift over time. So we were approached to see if we can kind of take advantage of the better time response of the 63 sensor and turn that into a sensor that's also calibratable in air. And the way we achieve that is we're taking it out of the flow path, or actually we're repositioning the sensor at the end of the flow path. So you basically think of the water as coming in here, going through the CTD, and then coming back out, and it's exhausted over the optical oxygen sensor in the new design. So that gives you kind of the best of both worlds, where you have still the advantage of the pump flow, so the faster time response of the sensor, but also the ability to do an in-air calibration. So at least that was the idea. And there was a whole knob project around that to really make that technology come to life. And as I said before, a lot of the difficulty is in really validating whether it actually works. So the way we approach that is we basically manufactured a specific Navis float that included 3 optical oxygen sensors. We had an Andera 4330 in here. I think it's really hard to see. We had the new prototype of what we call the SBS 83 sensor. And then we had the original SBE 63 sensor still in the float. And that really helps us to do intercomparison between the sensor and kind of analyze and evaluate their performance with regard to each other. So we were, even in the alpha deployment that you can see here, which was done off Hawaii on one of the Navis floats, you can see a pretty good agreement in the data after you correct it with the in-air gain between the two sensors. You can actually see that the Seabird 83 has a little bit less noise. I think it's shown in blue there than the Andera. So the original goal was really kind of to achieve the same performance as the Andera when it comes to the drift correction. And you can see that that's definitely something we achieved. We also noted that by integrating it in the way we did with the TC duct, with the flow loop, we actually get a bit of a better time response from the sensor. Obviously, there was a lot of evaluation done because the art community relies on sensors really working not just once, but over a long period of time. So you can see here's a little bit of a statistical analysis for the whole water column, where the 83 is shown in red, the histogram. I think they used the 63 as kind of the intrinsic comparison or kind of reference. And on the right side is more the surface water shown. So you see a little bit more variability there. But overall, there's incredible agreement between the two sensors. So that's really the takeaway here. So we're really happy with the performance. And this was even in the first iteration of the sensor. Normally, that's not something that you will find when you do go into the field, that it works so well right from the get-go. So kind of in summary, that version of the sensor launched at the end of last year. We are able to achieve agreement within 0.5% after the drift correction in air. The original goal was to be within 1% of each other. One thing that we've noticed is that because we integrated into the outflow of the TC duct, you get a slightly better time response that leads to a reduced bias in the oxycline by about, I would say, a factor 2 to 3 or something like that. What we found is that the air calibrations are repeatable, overall show a little bit of a lower standard deviation compared to the existing technology or state-of-the-art technology. Currently, these sensors are deployed on BGC Navis R&D floats that have been in the field for several years now, so you can really evaluate their performance over time. So that covers it for the first stop of the chemical part of BGC. Any questions on that? Yes?
When you implement that on an Apex of the 83, will that be, it will be the same setup in the exhaust loop?
Yes.
Yeah, okay.
Yeah, and we actually have a Navis float down in the booth if you want to take a look at it, because these were all prototypes. They don't quite look like that right now, but it gives you some idea of how they're integrated in the CTD head. It's just a slightly different form factor because it's on a Navis float, which has a different diameter. Yeah. You don't need it? you don't want it.
Nothing here.
It's too warm. Yes?
If you didn't perform the air calibrations on it, you just left it in the water for an extended period of time, would it perform as well as the earlier version of the oxygen sensor? Or is it actually requiring this constant air calibration to...
No, it would work the same way because it's really the same internal technology as the 63. It's just taken out of the flow loop.
Okay.
Yeah. Maybe it doesn't have quite the same time response because it's sitting in a different part of the TC duct. Does that answer your question? Should I repeat the question? Okay. So normally I would stop here, like I said, because these are really all the BGC sensor improvements that were launched. One new product, 3 improvements on existing technology that were released over the last couple of years. But given the number of questions I got on pH, I thought it would be valuable to at least give you some insight on where we are with that technology right now. Okay, so let's get started. I should probably say that when I say pH measurements, I'm not talking about glass bulb measurements right now. I'm talking about solid state pH measurements. Who has used solid state pH sensors? Thank you. Awesome. What kind?
We have a deep sea river plant.
You're a Seafox?
No, we stored Martzburg.
Oh, Todd Martzburg.
Yeah, and
Okay.
then we have Seafox.
You have a Seafox too? Okay. So what's shown here is really the pH sensing is achieved by 2 elements. On the left side, you see what's called the ISFET, that's the ion selective field effect transistor that measures the H+ ions, and it's paired with a silver-silver chloride reference on the right side. You can see that. Just to give you an idea of how, with the size of that sensing element, it's smaller than 2 by 2 millimeters, so it's tiny. And the mechanical tolerances to assemble these sensors are better than 1/1000th of an inch, or 10 to the negative 4 millimeters. So they're incredibly tight, very difficult to manufacture from the mechanical assembly side. On top of that, it requires 3 different types of calibration to actually get that sensor to perform at the level that we need it to perform. So it requires a temperature calibration, it requires how that element responds to pressure, and then we calibrate it with regard to chemical potential on pH. So it's a very involved process to get this sensor actually from the beginning of manufacturing to the final version, and typically that takes over the course of somewhere between 4 and 6 weeks just to do one run of that. Do you have any idea of how many sensors come out at the end of that process that actually meet our accuracy requirements? Any guesses? 10%? It's actually higher than that. It's between 20 and 30%. Yeah, but it's incredibly low yield, so to say. So we have this technology implemented in 2 different types of instruments. We have the Seafox, that's basically, you can see here, it's combined with a microhead. The sensing element is here shown by the green arrow. And it's also integrated on a Navis float. You can see it on the very right side. It says pH there where the green arrow is. That's a profiling instrument, but it's typically profiling very slowly, about 10 centimeters per second. And on the Seafox application, it's really used in a moored mode. The idea we had for pH improvements, given the yield and just the difficulty of manufacturing, were really to improve the field reliability. You can imagine if you seal a sensor that is only 2 by 2 square millimeters with O-rings, you can barely see the O-rings. And anybody who has handled O-rings and need to make sure they're clean, you can imagine how we have to deal with that. It involves microscopes and things like that. The other targeted improvement was really about reducing the calibration time and increasing the yield, because that's something that if you only get 2 out of 10 or 3 out of 10 sensors at the end of 6 weeks, that's really not scalable well. The other thing we wanted to do is improve the sensor response time to potentially use it more in faster profiling applications. So let's talk a little bit about how we approach this. We thought one way to really relieve some of the mechanical stresses, because the sensor's going down to 2,000 meters and a very tiny O-ring has to seal against the very small surface of the sensor itself. So there are a lot of stresses involved, is to pressure compensate this sensor. So the way you do this is you basically, on the left side, you see the existing design that is non-pressure compensated, and you add a chamber that you fill with oil that is open to the environment, and by doing so, it basically back pressures the backside of the ISFET sensing element and reduces the differential pressure to 0 between the two. So the actual solid state element is not flexing anymore as you go down or change pressure. We got this technology to work. We actually have a. If you look at how you typically calibrate, I've talked about the 3 different steps of calibration for the ISFET sensor. There's the temperature part. What's shown here is the pressure part. So what you see, it's a fairly nonlinear calibration, so a nonlinear response of the sensing element to pressure. And this is for the original design that's not pressure compensated. So you can kind of see here it's just a not very linear response as a function of pressure. One thing you don't see in here is that there's an area very close to the surface here that is not well modeled currently. So even by increasing the resolution on the pressure steps that you do, you should kind of see on the middle plot, although you have to kind of rotate it by 90 degrees because we changed orientation here. So I hope you can do that. But you can see how highly nonlinear that becomes. So one of the challenges was, what kind of order of polynomial do you use to even model this in the first place? And I can tell you that this kind of behavior pretty much varies from batch to batch in terms of the chips and the components we get to assemble this. So it becomes very difficult to standardize the calibration process in terms of what order of polynomial do you use, what kind of method do you use to actually characterize this behavior. This is something that is much improved if you look at the pressure compensated version of that. So you can see that if you use the pressure compensated design, it completely linearizes the response to pressure. So that's a huge improvement. It's much more scalable in terms of your calibration methods. And that's the path we're pursuing right now. We did evaluation of this new technology on a glider, a Embari glider, a spray glider, to kind of see how it performs in the field. And in that application, you actually basically sampling on the downside and the upside of the cycle, where on a typical float application, you only sample on the ascending side of things. But initial results were for deeper regions, agreement between the Canyon B model of less than 10 milliph. So that's actually quite good performance here. Now, one thing we did notice that as we were doing this glider deployment of the sensor that we hadn't done before, there were some interesting features in the profiles. At the end of the profile, you can kind of see this where the green circles are. You can kind of see these little hooks there. That's basically what we call hysteresis effects. As you're going up, basically the time response of the sensor is not well characterized, and basically it's not responding fast enough. And we attribute this to not the ISFET component, but the reference component of the sensing element. So we did basically an evaluation of if we change the reference electrode to a faster one and see what happens. So we did another deployment of gliders with a faster reference, the same basically ISFET sensing element, but a faster reference, and the hooks disappear. So we have the additional challenge of not only having a very tight tolerance design on the ISFET sensing technology, we also have kind of batch-to-batch variability on the reference side that we have to take into account when we calibrate the sensors. So this is kind of where I wanted to stop. Any question on pH? No.
Sorry. Yeah.
Yep.
When do you see this being available to people?
I was afraid you're going to ask me that question. Let's put it this way. We have the pressure compensated sensors deployed on some R&D floats right now. But not all of the deployments are successful. That's typically how it works, you know, until we achieve a level of consistency, we don't really have a timeline. I'm not sure if you're aware of that the manufacturer of the ISFET actually discontinued this design. So I'm not sure if this is common knowledge, but we found out about that at the end of last year, as we typically place our yearly order for that the technology or for the ISFET itself was not continued. Thankfully, to the kind of efforts of government agencies, they were able to convince Honeywell to restart the manufacturing of this technology, given that it's used widely across the ocean technology sector, you know, in terms of measuring pH. But for the time being, we only have tentative timelines in terms of what supply will be. So it's that even complicates the prediction of when new designs will be released. We're pursuing alternative ISFET solutions, but we have not been able to evaluate those yet. You definitely earned that scarf. It's too warm. Okay, so this kind of brings us to the end. So the things that I want for you to take away is what kind of biogeochemical improvements have been implemented. So we have talked about the new version of the HydroCat EP-V2. We talked about the LED ACS, the additional 435 nanometer wavelength on the ecofluorometer. And we have discussed the new product launch of the SBS 83 and hopefully gotten you a little bit of insight into what's happening with pH. Any questions? If not, I thank you for your attendance here. Really appreciate it.